Hello everyone. Before we look at the statistical properties of OLS estimates, let us look at their numerical properties. So by the end of this lesson, you will understand the numerical properties of the OLS estimate. The regression coefficients obtained by the OLS method are called least squares estimators. These least squares estimators have numerical properties. So according to Davidson and McKinnon, numerical properties are those that hold as a consequence of the use of ordinary least squares, regardless of how the data were generated. So these are the numerical properties. 1. The OLS estimators are expressed solely in terms of observable sample quantities of the dependent and independent variable. 2. They are also point estimators. That is, given the sample, each regression coefficient will yield a single value of the relevant population parameter. 3. The sample regression line can be easily obtained once OLS estimates are obtained from the sample. Now, the regression line in itself also has the following properties. It passes through the sample means of X and Y. This means if you draw the regression line or the line of best fit in the scatter diagram, you will find out that this line passes through the mean of the dependent variable and that of the independent variable. Also, the mean value of the estimated Y equals the mean of the actual Y. At this point, we will have to look at some kind of proof to show that indeed the mean value of the estimated Y equals the mean of the actual Y. So the first thing that you need to do is you need to recall the formula for calculating the intercept, which is beta 1 hat equals Y bar minus the slope coefficient beta 2 hat multiplied by the mean of X. And we would have to go ahead and look at the sample regression function. So the sample regression function is given by yi hat equals beta 1 hat plus beta 2 hat xi. So all we have to do is now substitute the formula for calculating the intercept into this sample regression function. So we are going to have yi hat equals then y bar minus beta 2 hat x bar and then plus beta 2 hat xi. Now you can see that on the right hand side we have beta 2 hat and beta 2 hat, so we need to factorize that one out. So we will have yi hat equals y bar, then plus beta 2, we factorize that out, and we will have xi minus x bar. So at this point, all you have to do is, if you want to find the mean of the estimated Y on the left-hand side, you would have to sum both sides and then divide by the sample size. That is how we calculate the mean. So in which case, we will simply go ahead and have the sum of yi hat divided by the sample size on the left-hand side. Then on the right-hand side, we will also have the sum of y bar plus beta 2 hat xi minus x bar divided by the sample size. So on the left-hand side, the sum of yi hat divided by the sample size will give us y hat bar, which is the mean of the estimated Y, and that equals, now we distribute the sigma notation through the terms in the bracket. So the sum of y bar, notice that the y bar is a constant term, so the sum of y bar is simply n multiplied by the y bar, and this will be divided by the sample size down here, then plus, we also have beta 2, which happens to be a constant, so that will also go out like this, beta 2 hat, and then we will have the sum of the term in the bracket, which is xi minus x bar, and this is also divided by n. Now, if you recall from the previous video, you realize that the sum of the deviation of x. The sum of the deviation of x equals 0. So in which case, this entire term here is going to be equal to 0. And this n term will also cancel out the n term at the numerator. So we will now end up getting the result to be y hat bar equals y bar. So this proves that the mean of the estimated y equals the mean of the actual y. Also, the mean value of the residuals is equal to 0. So if you recall from the derivative of the sum of squared errors with respect to the intercept, we ended up getting this part here. So let's extract that to prove that the mean value of the residuals is also equal to 0. So I would go ahead and write that here. So we have the sum of yi minus beta 1 hat minus beta 2 hat xi equal to 0. Now, at this point, we will have the sum of, let's separate the terms out. We have yi minus, then this would become beta 1 hat plus beta 2 hat xi, and that equals 0. And if you recall, the beta 1 hat plus beta 2 hat xi is simply yi hat. So we will go ahead and have the sum of yi minus yi hat equal to 0. And again, if you recall, the residual term ui hat is simply the difference between the actual y and that of the estimated. So this would simply be the sum of, so let's go ahead and write it this way. So these two terms would be the residual term. So we would go ahead and have the sum of ui hat equal to 0. And so if you go ahead and divide the left-hand side by n and the right-hand side by n in order to calculate the mean of the residual, you will end up getting the ui hat bar, which happens to be the mean on the left, and that equals 0 divided by n is simply 0. So we also find out that the mean value of the residuals also equals 0. Again, the residuals ui are uncorrelated with the predicted y. So here also we need to have some kind of proof to show that this is indeed satisfied. So we will again start with the sample regression equation. So the sample regression is given by yi equals beta 1 hat plus beta 2 hat xi plus ui hat. Now I would like to call this my first equation. And I would like to find the mean sample regression. So this means that I would have to sum the terms and divide by the sample size. So I would have the sum of yi divided by n on the left-hand side. Then on the right-hand side, we will also have the sum of all these terms, beta 1 hat plus beta 2 hat xi plus ui hat. And then we divide this entire side by the sample size. And so the sum of yi divided by n simply equals the mean of y, which then equals now the sum of beta 1 hat, and beta 1 hat is a constant term, so that is going to be n times beta 1 hat, and we divide by the sample size, plus now we have beta 2 hat xi, so that would be beta 2 hat out, then the sum of the variable itself, xi, we also divide by the sample size n, and then plus the sum of ui hat also divided by the sample size. Now, there is something quite interesting. From our previous derivation, you realize that the sum of ui hat equal to 0. And here we went ahead and even divided by n to find the mean, and the mean also equal to 0. So this identity holds that the sum of ui hat equal to 0, and the mean of the residual is also equal to 0. So in that case, this term here equal to 0. So we will end up now getting the result to be y bar equals beta 1 hat, because the sample size at the numerator and denominator cancel out, then plus beta 2 hat, sum of xi divided by n is simply x bar. So this is going to be the mean sample regression, and I would also like to name this as my second equation. Then after that, I would like to go ahead and find the deviation from the mean. So that means we will have to take the actual sample regression and we subtract the mean from that to get the deviation from the mean. So in this case, let's use a different ink. In this case, these two terms, yi and y bar, so simply we are just saying equation 1 minus the second equation. So we are just subtracting equation 2 from 1. So yi minus y bar, that is going to be equal to beta 1 hat, then minus the beta 1 hat from the mean. So beta 1 hat, then plus beta 2 hat xi, and what was the mean? It was beta 2 hat x bar, so minus beta 2 hat x bar, then plus the residual term from equation 1 minus the residual term in the mean sample regression is 0, because the sum of the error term divided by n, which happens to be the mean, simply equal to 0 as it was proven. So we have yi minus y bar, and that equals beta 1 hat minus beta 1 hat will cross out, so that will become 0. Then here we are going to have beta 2 hat, we can factorize that one out, and we have xi minus x bar, then plus ui hat minus its mean, which is 0. Now, at this point, we will have to adopt the fact that the deviation of y, so yi minus y bar, simply equal to the lowercase yi, and then also the lowercase xi is the uppercase xi from its mean. And then the lowercase ui hat is the uppercase ui hat from its mean of 0. So once we express these identities, we can now have yi equals beta 2 hat lowercase xi plus ui lowercase hat. And this is the deviation form. So this is the deviation form of the sample regression. So we call this the deviation form. And I would like to call this my third equation. And in that case, this looks very similar to the equation 1, except that the equation 3 is in its deviation form. So you can most likely see that this second term is lowercase yi hat, which is the estimated y in deviation form. So we can go ahead and also write something like where the yi hat equals the beta 2 hat lowercase xi. So that is also going to be the estimated y in deviation form. Now, using the estimated y in deviation form, which we had to be. If we want to prove the fact that the residual term is uncorrelated with the predicted y, then we will have to multiply each term on the left and right by the residual term and sum through it as well. First, we are going to have yi hat multiplied by the ui hat, and that would mean that we would also have beta 2 hat xi also multiplied by the ui hat, all in deviation form. And we will have to apply the sigma notation to both sides of the equation. So this would yield sigma yi hat ui hat, and this equals, because the beta 2 is a constant term that comes out, and then sigma lowercase xi ui hat. And once we have this, from the third equation, you will find out that the residual term ui hat simply equals the actual yi in deviation form minus the sample regression function in deviation form. So it's going to be just making ui hat the subject to find the residual term from equation 3. So we will go ahead and substitute this residual term into this very equation. So here we are going to have the result to be the sum of yi hat ui hat equals beta 2 hat the sum of xi, and this would multiply the residual term, which is the actual y minus beta 2 hat xi from the third equation. So let me indicate something here as from equation 3. So once we have this, now the sum of yi hat ui hat now equals, we go ahead and expand the bracket. So we are going to have beta 2 hat the sum of xi multiplied by yi, then minus, now we would have beta 2 hat squared, then the sum of xi squared. So we go ahead and expand this bracket like that. Now there is something that I need to prove here for you to see that on the right hand side, the term on the immediate left and that of the right are the same. And so let's try to separate that proof here. So you will find that the beta 2 hat sigma xi yi, but we need to remember that the beta 2 hat equals the sigma lowercase xi yi divided by sigma xi squared from the method of ordinary least squares derivation of the slope coefficient. So that is the formula. So I will put that back here. The sum of xi yi divided by the sum of xi squared, and then multiplied by the sum of xi yi. Then how do we then express this term to be the same as this term right here? So all we have to do right now is, there is something wonderful I want to do here, and you would observe I have not really done anything except that if I divide this term by the sum of xi squared, and again multiply by the sum of xi squared, I have not really altered this particular expression, because this sum of xi squared as the denominator will now cancel the sum of xi squared, which is also multiplying. So that yields the same sort of expression. But we introduce this concept in order to build our intuition right here. So all that we are trying to do from introducing this division by sum of xi squared and multiply by sum of si squared is simply to take this expression here, and that equals the beta 2 hat. That is the formula for beta 2 hat. And then this term also divided by sum of xi squared is also the same formula for beta 2 hat. And then that multiplies the sum of xi squared. So you end up observing that beta 2 multiplied by beta 2 is simply equal to beta 2 hat squared and then the sum of xi squared. So in which case we have proven, so let me use another ink. In this case, we have proven that beta 2 hat sum of xi yi is identically equal to beta 2 hat squared, the sum of xi squared. So by proving that, we can now go back here and write the sum of yi hat ui hat equals, then this term is the same as beta 2 hat squared sum of xi squared, then minus this term that is also on the right, beta 2 squared, and the sum of xi squared. So what really happens right here? Very obvious. The sum of yi ui hat simply equal to 0. This is what we mean by the correlation between the predicted y and the residuals is simply equal to 0. That means they are not correlated. They do not have a relationship. So this is the proof for this particular property of the regression line. Again, the residuals are also uncorrelated with xi. So somehow, when the residuals and the xi are brought together, they should also amount to 0. So we'll pick it up from where we differentiated the sum of squared errors with respect to the regression slope coefficient. So we will pick it up from this term here. So here, I would just go ahead and write the sum of yi minus beta 1 hat minus beta 2 hat xi multiplied by xi equal to 0. So we know exactly what we have done before. So yi minus, then these terms, I put them in the bracket. So it's going to be plus beta 2 hat here, xi, multiplied by xi equal to 0. So we will have the sum of yi minus these two terms would yield yi hat multiplied by xi. And we also know that this term is ui hat, which is the residual term. So we go ahead and write the sum of ui hat multiplied by this xi simply equal to 0. So this is also the proof that the relationship between the residuals and that of xi is simply 0. So there is no correlation between the residual term and that of xi. So at this point, in the next lesson, we will look at the statistical properties of OLS estimates. In particular, we will examine the assumptions underlying the classical linear regression model.